Are we good? Everyone seeing me here?
Mm-hmm.
I think so. Let's bring up the chat window so I can see what people are saying. Right, so if you were fortunate enough to have your server running, you should see, and you were in the notebooks directory, you should see all these things. And the first step to actually getting this stuff running for what I'm about to talk about is to open one of these notebooks called Setup Monday Module 1, although I guess it's not Monday. This is something that France set up because I was a bit late getting all my notebooks in, and they're not in the normal repos. But to pull all the things that I've been producing, and France, maybe we can hear you typing.
Yes, totally.
You need to open up this notebook and run it. And basically, it has 3 more git clone commands that will pull a series of notebooks that I will be using today and tomorrow. So the first step would be to execute this, and it will crash for me, but I did it this morning, and you see it pulled in 3 sets of notebooks, and they all end up in this module 1 directory here. The one that we're looking at today is interpreting InSAR. So if you get through all of that and manage to clone this this directory, this is what you'll find. Now, I guess people are still having trouble getting this far, but there are potentially things that we can talk about even so whilst you're waiting. Okay, so that notebook really doesn't have any executable elements in it. It's just a kind of a placeholder for a bunch of things. And what we're going to be looking at is an interferogram of an earthquake. This earthquake happened in Turkey in, yeah, you can actually get them yourself. Let me see. Interpreting InSAR. So the GitHub link is this. And that might be a solution. So you can go to that web page and you'll be able to basically download the code from this button here. You can also git clone in a local directory if you're familiar with command line things. Either way, you'll end up with all these files. Maybe the one that you won't be able to look at easily is the Jupyter notebook, but you'll get all the files, which are kind of what we're using anyway. As I say, we have an interferogram of an earthquake. This earthquake happened in Turkey in 1995. Magnitude 6.4 earthquake near the city of Dinar. And I provide you with some files in this repo or in this folder. One of which is the interferogram, and you can click on the link in the notebook, and you'll get this PDF. You'll also notice that I have made a PNG file of it, which is in the notebook, so you can just look at that. The PDF has a caption which describes various things about this interferogram. You'll see, for example, that it says, each cycle of colors from blue to yellow to red indicates an increase of distance between the satellite and the ground of 2.8 centimeters. So that's the information you need to be able to interpret this interferogram in terms of which way the ground moved. As I say, I've become very conscious of the fact that you need to say these things in figure captions because there is no uniform sign convention that people use. In this case, blue to yellow to red, one phase cycle is an increase of distance away from the ground away from the satellite, which means that this is a range change interferogram.
Gareth, can I briefly interrupt you? Just in maybe that's more in defense of our system. But oddly, the issue that we are having is actually that AWS has run out of the machine instances that we are requesting. So AWS West currently has no available machines, which sounds crazy because the cloud is the cloud and is unlimited and you can do whatever you want. Apparently that's not true. That's what we learned today. So we're working on it on the back end, but it's not the ASF system. It's the cloud provider has run out of machine instances.
So now this doesn't require any computational resources to run any of this stuff. So would it be okay for people to run one of the smaller instances, or are none of those available either?
I'm going to try
it. You should be able to do the small instance. If that's no heavy processing, if you can't log in, choose the regular regular setup, and that should start hopefully. Maybe Paul, maybe you can verify that.
I'm about to do it. Yeah.
You're going to want that though for tops this afternoon, I guess.
Yeah. So somebody needs to yell at Amazon.
Well, JPLC, Tom Soderstrom just went there, so you can yell at him.
Maybe that's why it broke.
You want the link to interpreting InSAR? Well, it's in the module 1. If you're in the system in the notebooks folder, UNAV Co-InSAR. My system isn't.
And now I can't connect to OpenSAR Lab at all.
Right, mine is. I'm clicking links and nothing is changing. Interesting. Well, if you can.
What did you do, Paul?
I didn't do anything. I didn't do anything.
Okay.
Well, even if you're even if you can't get the notebook running, we can at least look at the interferogram through the GitHub repo. So maybe we should do that whilst we're waiting.
So Gareth, they can go to the GitHub repo, download these files, and do the exercise on the screen, basically, without access to.
They can, and I can show you another thing you can do as well, because we are actually what we're planning to do with this interferogram is to unwrap it manually along this profile. Here, you can see this profile from X to X prime. Another thing that comes with this repo is a grid, like so, onto which you're asked to draw your unwrapped profile. So what we want to turn the interferogram. No, server cannot be established. Connection. So you can see the fringes on this interferogram. We want to turn that into a continuous displacement profile along this line, starting at 0 at the end and ending up wherever you end up. That's the idea. So we know that each phase cycle from blue to yellow to red is 2.8 centimeters away, a movement of the ground 2.8 centimeters away from the satellite. We're going to assume that all of the displacement is vertical. That is an assumption. It's a reasonable assumption for this type of earthquake, but it's not exactly correct. But suspend your critical faculties, I guess, for that part of this exercise, and draw this profile. Now, in terms of like how you can do this, if you can get into these into the repo, you you can download PNG files or PDF files of the interferogram and the grid. The way that we originally run this exercise is on paper. If you actually have access to a color printer, you can print those two PDFs out, and if you print them the same scale, the profile line of the interferogram is exactly the same length as the grid that you're supposed to draw the profile onto. But of course, we're not all in the same room, and we don't have access to UNAVCO's printers. So what I suggest to do instead, is everything running again now? Maybe.
Yeah, I got my instance.
Yes. So I started your instance on the regular machine, Paul. So you are up.
What do you mean you started it? I thought I started it.
Yeah, I started it for you.
He has the power. The tool.
Okay.
So if your server is not up, please raise your hand, and I'm gonna get you set up and then let you know.
I'm not connected. It says.
So refresh that notebook. Okay, launch server. Yep.
Yeah. Okay.
And that should go. Haha, now of course new
You have to wait for everyone else.
servers are spinning up, but yes. So if you raise your hand in WebEx, if you don't have a running server, then I'll get it started up for you.
Meanwhile, I can show you what I have in mind for this exercise. Oh, I want interpretation. Right. So, as I said, the profile line and the grid should be the same size, and if you print them out. But anyway, what I have in mind for you to do, and if you don't have access to a printer, is to unwrap it on a computer, and you can do this various ways. The two PNG files that are plotted here are in the GitHub repo, and you can download them. The color interferogram and the profile in black and white. You can download those to your local machine, and you can set them up in any image editing software that you have on your computer. PowerPoint would do it, CorelDRAW, Illustrator, any of those. But for those of you who don't have access to that, I kind of hacked together something you can do in a browser window. So this is another option. And I guess.
Sorry, Garrett, where is this stuff on the server? I missed that part because I wasn't up.
It is. All right, we'll go through that part again.
Yeah.
Yeah, there's a notebook in the UNAFCO InSAR folder.
Okay.
It's called UNAFCO InSAR Setup Module 1, Monday
Okay.
Module 1. If you run that, it's going to pull everything in.
And it's all in a directory called Module 1. If you run it.
Setup module.
We are coming back to life. So we have now 79 people that are on, I think.
Good.
Super.
Gareth, you should be on.
You're
You're almost on.
I'm very close.
Expand the event log and let me just see.
In there.
Put in the image. So it should be succeeding here shortly.
Got it.
Anywho, what I had in mind was you could put the profile against the grid like so. You can do it yourself, as I say, in PowerPoint or Illustrator or any software that you have that can manipulate images. Pull the two in. And what you're trying to do is to go along this profile line and estimate what the displacement is at every point along the line. In the notebook itself, when I actually have access to it, That's cool. There are actually some questions to answer before we do the unwrapping along the profile. So if you read through this, the first thing you're asked to do is to estimate how many fringes of displacement there are on either side of the profile. And we use some geological terminology, which I guess some people will not be familiar with, hanging wall and footwall as the sides of the fault that you're on. The surface rupture of the fault, where the fault met the surface, is this black line here on the interferogram, and that represents where the fault broke at the surface, and essentially everything on the right of that, to the east of that fault break, is what we call the footwall side of the fault, and everything on the west side of it is what we call the hanging wall side of the fault. These terms originate from mining, and in as much as the footwall is the part that you stand on, and the fault hanging wall is the thing you hang your miner's lantern from. And so the fault actually dips, has an inclination to the southwest. So if you were on this side of the fault, the block of rock above the fault would be the hanging wall, and the block of rock below the fault would be the footwall on the right. Anyway, the first task is to count the number of fringes and convert that into a displacement. And as I said, 2.8 centimeters of movement away from the satellite is one fringe. So that's your first task. You count the fringes on either side of the fault.
Gareth, can I ask something real quick?
Yeah.
Just in terms of hanging wall and footwall, that's always relative to the motion on the fault, I presume, right? Not like east and west per definition.
It's it's relative to your position relative to the fault. The fault is a surface, and the fault has what we call a dip to it. It dips from east to west, so it's tilting to the southwest in this case. So there are two blocks of rock, one above and one below the fault. The block above the fault, which would be on the southwest side, is the hanging wall, and the block that you would be standing on beneath the fault is the footwall. And so if you project where the fault goes to the surface, everything to the east of the fault, to the northeast of the fault, will be on the footwall part of the fault, the footwall block of rock. And everything to the southwest at the surface would be above the fault, and be on the hanging wall. Does that make sense?
Yeah, I think so. I was just confused because it sounded like you were just saying east of the fault, east is the footwall, and west is the hanging wall. But I presume it really depends on the orientation of the fault. It does.
In this particular case, with the orientation the fault has, that is true. But yes, it's not a general rule. East equals footwall, no. Geologically below the fault, I guess, is what we say for footwall, and geologically above it. So here's a question about 1/2 wavelength for a cycle of fringe. Why is it not the full wavelength? That's because the radar takes a two-way path between the satellite and the ground. So if you move the ground 1/2 a wavelength away from the satellite, then the two-way path from the satellite to the ground and back again is increased by a full wavelength. So that's one total phase cycle, 2 pi, one wavelength of two-way path movement equals 1/2 wavelength of surface movement. Does that make sense?
Yeah, 4 pi over lambda is 2 pi times 2 over lambda, so effectively lambda is divided by 2 there in the problem.
I meant to say that yesterday, so I forgot.
Yeah.
So that's due to the ping pong mode of, right?
Yeah, you could argue that. It's really just because of the two-way path length, but that's correct.
Okay, so the first task is to count the fringes on either side. Has anyone managed to do that? It gets a bit hairy in this area. I like 21, but sometimes I count it and I get a different number. So. And one additional wrinkle is I say that you should start counting from this point here, and this is actually not on a fringe boundary. It's about halfway between one fringe and the next. So ideally, you would add half a fringe to the number that you come up with if you started counting here. So I assume 21.5 fringes, and someone can tell me what that is in centimeters or meters. What about on the other side? A bit trickier. So on the footwall side, I have to guess a 2. I'm going to say that the end of the profile is at 0 again. So I like 2.5. Yeah. So you can see maybe a boundary between red and blue here with the ISA, and then another one here, and maybe you get all the way to dark blue again. So that's half a cycle, maybe to here, then a whole cycle to there, and another whole cycle to there. So that would be 2.5. Okay, great. That's a good start. So you can estimate what that is in terms of displacement as well. That's a bit easier, actually. You know what that is in displacement. That's 7 centimeters. .5 times 2.8 centimeters. So 7. Okay, and then what are the directions of displacement on either side of the fault? That's the last part that you're asked to do for each side of the fault. So on the hanging wall side, on the southwest side, what's the direction of movement of the ground? Is it up or down? And how would you tell? Right, and again, the key is in your figure caption here. Each cycle of colors from blue to yellow to red indicates an increase in distance between the satellite and the ground. So every time you go from blue to yellow to red, you're going down 2.8 centimeters. Down, then more down, even more down, 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 down. So yes, the southwest side of the fault, the hanging wall side, is going down. What about the other side? Okay, so how would you tell? Red to yellow to blue is the opposite of blue to yellow to red, right? So if blue to yellow to red is going down, red to yellow to blue should be going up. Does that make sense? So if you start out here, you have red, then yellow, then blue, then red, then yellow, then blue. That implies that if you start out here and count inwards, you should be going up. Do people see that? I see a mixture of people saying it's going down and people saying it's going up. The key with all of these things is to start in a location where you know there's no movement. So for the hanging wall side of the profile, we started out here, far away from the fault, and we could see that as you got closer to the fault, the ground was moving down. The reverse should be true out here. Out here, we can say at the end of this profile that there's no displacement, or at least just take it from me that basically from here on out, if the interferogram carried on to the northeast, you wouldn't see any more fringes. But as you move and count inwards along the profile, you can see that you're going red, yellow, blue, which is movement of the ground towards the satellite. So as you're moving in this way, the ground should be moving up. So in the area which is incoherent, which is in here, where we don't have any information, there's a reason for why there's no information there. Basically, the ground was broken by the fault moving, and we would expect a discontinuity in the phase at this location, because as we see, one side is moving down, the other side is moving up. There's not an easy way of joining that up across the profile. And to Nathan's question, yes, you do count from the edge of the profile and inwards. In this particular case, the phase is discontinuous through here, and so if you try to continuously unwrap through here, you would make a mistake. You can actually see if you move further out that the fringes are continuous in the far field. You can go from your first positive range change fringe and your first negative range change fringe, and you can actually go from one to the next, but only out away from where the surface was broken by the fault. If you go through the middle, there's a discontinuity in the fringes.
Because if they were continuous, we would expect a reversal, right, of the color gradient? I mean, they can't be, but like, does it flip when you go around?
If there wasn't a discontinuity here, then ground would keep going down as you go to the northeast. But because you can't see a connection through here, you shouldn't necessarily assume that the deformation is continuous. Because even if the point on immediately on the other side of the fault was that is the highest point, and everything as you go to the northeast is still down from there. That's something that would confuse you, I think, and does confuse people if you just keep going counting fringes as you go to the northeast. The key is that the phase does not connect through here, so you can't actually connect this to that. That's why it's safer to start at the edge and work inward, because then you don't try and unwrap across the discontinuity. Because if you went around a path around the edge, you could see that this fringe and this fringe are only one apart. But if you do it across here, that fringe on the profile line is located here, and the other fringe on the profile line is located there. And there's a whole lot of stuff that happens in between those 2 points if you go along that profile line, which doesn't happen around the edge. Which is to say, your unwrapping algorithm would probably do fine with this. It would see that this is all connected through here, that this is one fringe up and that is one fringe down, and then it would unwrap along this path until it couldn't go any further, and it would unwrap up here until it couldn't go any further, and it would show that there was a large difference in phase between here and here, which you can kind of see if you work around the edges. So anyway, what I have in mind for you to do, and if you have your notebook up, then you can do this, is either download the files, which are linked further up here. You can download the PDFs or the PNG files, and you can load them into something like Illustrator or PowerPoint, or you can try and do this on the web interface in Google Draw, which is clunky though. I warn you, but I put a link in here to it. You can click on that, and it will load these things in, and you can make a copy for yourself. So you go follow that link and click on make a copy, and you can save it to your own personal space. If you have a Google account, I think that should be fine. For those of people who don't have access to Google things, I had another thought. There are other tools that you can use. There's this file at this website called Draw.io or diagrams.net, and you can open a file in that, and I provided a file that should open in there, which is this thing, which will download if you click that link. And you can open that diagram file in this website, and it's the same thing. And I provided a line for you to move, so that you can basically move it to the point where you have a fringe boundary. And then I provided a dot, which then you can make copies of and try to move into place. Yeah, so it changes. Either way you do this, this is a bit annoying because it distorts your line. This is why I would do this in PowerPoint if I had access to it. But you can kind of move these dots into place and, you know, whatever, to the right spot on the axis here. It's much easier to do on paper, but I appreciate that many people do not have access to printers. But in theory, that first half fringe should be 1.4 centimeters of deformation, so it's going to be very close to 0. But that's the idea. And then you would just keep going every time your line crosses a fault, crosses a fringe, sorry. And you can see that you're going to have to do some eye of faith interpolation in some places because the interferogram isn't always coherent everywhere. But yes, you can keep going and adding each successive fringe interval to your profile. That's the idea. Does that make sense? You can do this in whichever web interface you are most comfortable with, or on software on your own computer. And from the quietness of the internet, are people just getting stuck in here? I find that the Google Draw interface is not very it's not very precise. Doesn't allow you to put things in exactly the right spot. So if you have a kind of a perfectionist streak, you're meant to do it now, so we can talk about it. We have another 15 minutes, even with the web outages or the server outages. You should be able to get this done. In the notebook, there are a few suggestions. One is that, oops, don't double click on it. Just trying to highlight it. At 2.8 centimeters per fringe, 2.5 fringes is 7 centimeters and 5 fringes is 14 centimeters, which means that once you get into the area where there's lots of fringes, maybe you should just count every 5 and add 14 centimeters to the profile rather than trying to count every single one. And as I said, you will come unstuck if you try and go from try to go right along the profile line and keep adding fringes. I would advise starting at either end of the profile and counting in until you can't count anymore. And assume that the end of the profile didn't move. Has anyone managed to do the whole profile yet? Well, let me know when you're done in the chat, so that when a good number of people are done, we can look at something. Maybe something else to look at. Okay, so people are starting to finish. For those of you who are done, you have the option of having a look at this interferogram in its geographical context in Google Earth. Now you can do that in the web browser. This is another cool thing. In terms of the files I provided in the repo, there is an interferogram file that you can download as a KMZ. So if you were to do that, then you can go in here, and which just happens to be on Turkey. How about that? And you can make projects by import a KML file from Google or from the computer into the web browser, and you can see what it looks like in its geographical context. So you can look at it in perspective view or something like that. You can see that on the footwall side of the fault, on the northeast side of the fault, you see the topography in that area is actually uplifted. There's a range of mountains. If you turn off your interferogram temporarily, you'll see that some of the decorrelation you get in the interferogram is because there are lakes and agricultural areas on the lower part of the on the ground, the downthrown side of the fault, if you were a geologist. Some geological terms. So that should inform some of the things that you interpret about the interferogram. You would expect that the side, perhaps the side that on higher topography is also being uplifted in the earthquake. And similarly, the side that is on the more depressed side of the topography is the part that's going down in earthquakes. The fact that you have lakes on the hanging wall side of the fault is an indication that the ground is being pulled down by tectonics in this area and subsiding, and so it's getting filled in with rivers. Anyway, if you're done with profile making, you can have a play in Google Earth and look at these relationships between deformation and topography. In this particular case, we know where the fault is. From the question online, is the location of the fault usually known beforehand? I think the geomorphologists on the class would probably say that you would have some idea that there was a fault here just from the very abrupt change in elevation as you cross here. In this particular case, field geologists went here after the earthquake and actually mapped a surface rupture, actually mapped a surface break of a fault at the foot of this ridge. And in the notebook somewhere, I mentioned that the geologists measured 25 to 30 centimeters of offset on the fault. And note that that's not the same as what we see in the interferogram, right? If you look at the maximum displacements that we measure, they're bigger than that. And that's an interesting point that we can go into if anyone wants more of you have actually finished your profile. So we have 5 more minutes. What I'm going to say is that I did intend that this would be a homework exercise in that I didn't think we would get through every single thing in the time we have. I can show you my answer anyway, and then you can go off and finish yours and print them out. If you're doing it in Google, you can download as a PDF or a JPEG, and you can upload that to your homework directory like you normally have been. And all of the other ways that you have to work on this profile, you can produce graphical output. What I plan to do was show you my profile that I did in PowerPoint with the time I have left. Oops. So let's go back. So, okay, here's the same setup that we've been looking at. And how I went about unwrapping it. Yes, you start with 0 on the southwest side. Half a fringe is 1.4 centimeters. 1.5 fringes is 4.2. And then I think after that, 2.5 fringes is 7 centimeters. And I went to 5 after that. So about 21.5 or 22.5 fringes, depending on the strength of your eyesight and your ability to distinguish the fringes. So that's what you get if you start with X on the profile and you move inwards. This zone here is incoherent, so you can't unwrap through there. The fault is located there. And if you started at the other end at 0 and counted in, then you get a profile of uplift until you get to the fault there. In total, the total offset in vertical is around 70 centimeters. The exact number you get will depend, as I say, on exactly how many fringes you think you count. I'm not going to be very strict on the counting because I think it is difficult. But there are some features in the interferogram that maybe are of interest. As I said, there's a discrepancy between the total displacement that we measure on the interferogram, which is about 70 centimeters in line of sight, and we're going to assume that 70 centimeters in the vertical just for the sake of argument, and what we're seeing at the location of the fault here, which is about 30 centimeters. Note that the two measurements are not made in the same place. All right, that our total vertical from InSAR is estimated from this location and that one, whereas the fault is located here. So actually, there is a horizontal separation between where we're measuring maximum vertical motion and where the fault is, and I think that's important. What you can kind of see is that the fringes are starting to curve around in this area, and of course you can see them curve around up here. And if you were to enclose the, if you imagine that there was more coherent material here, you might actually see the ground start to go up again in this area. So in some sense, it's not inconsistent that the fault actually records smaller vertical offset than the interferogram, because it's quite likely actually that the maximum, well, we can identify that the maximum vertical motion is not located at the fault. There's actually some distance away from it. And where you have fringes that enclose, that implies that that the maximum vertical motion is actually buried, not actually at the surface. That's another thing that we can see from interferograms where you have enclosed deformation fringes. Yeah, 70 was my guess. I mean, it's in the ballpark of, as I say, between about 67, 68, and 70, somewhere like that, depending how many fringes exactly you count. So yeah, what we're identifying really is that the most of the motion of the earthquake was actually underground, and whatever made it to the surface is not representative of the earthquake. Yeah. there are some other questions. Actually, this is my another estimate here, and this is just from the teaching exercise I run using this. I should add that this whole exercise is one that I put together with some colleagues for UNAVCO for teaching about earthquakes using InSAR and LiDAR. And there's a lot more geological stuff in the exercise that we put together, which is linked from the notebook if you want to go and find it. I know that many of the people who take this class are not geologists, and therefore I threw most of it out for this exercise. But there's one more question that you're asked, which is, can you convert between the vertical height change, say, for the sake of argument here, 66 centimeters of vertical height change, and can you convert that to the motion of the fault? The fault is dipping in this area at 40 degrees. So with simple trig, you can go through and divide basically 40 degrees by the sine of, 66 centimeters by the sine of 40 degrees and get how far the motion was actually on the fault itself. And it comes to about a meter of the fault slip, which of course is much larger than we see at the surface, reinforcing that the fault was buried, or most of the fault was buried, and what you're seeing at the surface is just like the dying out of the fault as it gets to the surface. The reason that there's a topographic profile in here is for more geological stuff again. There's my profile versus the topography. You often hear people say that earthquakes build topography, and they kind of do, but they also kind of don't, because if you had multiple earthquakes adding up to be the topography, you would expect the topography to look more like this profile line than it does. So again, for like the three geologists in the audience, what you would expect in the long term is not just the earthquake, but the sum of the earthquake plus the interseismic phase of fault loading. And in fact, what you would expect the whole earthquake cycle to look like would be more like a step function. It's more like this. So in between earthquakes, the crust is bending in such a way that when you add the earthquake to the loading, you would get something more like that. And still, that looks a bit more like the topography, still not exactly like the topography. And the reason the two are not the same is because of other processes that occur geologically, such as erosion of the footwall. So you erode the back of this mountain, and then it doesn't match the long-term profile anymore. And then sediments will fill in this basin down here that you formed tectonically, and that's why there are lakes here. And there's sedimentary deposits, which mean that it doesn't look like the long-term tectonic cycle. But I don't want to belabor that point because I